Good morning, everyone. My name is Yijiang. I'm from Georgia Tech. Today I'm going to talk about an efficient branch and price approach for solving the flight gate assignment problem. This is a joint work with Professor John Paul Clark and Professor Shantanu Day. So why are we doing this problem? So there's a growing trend in the past decade in delay costs, as FAA in 2019 has reported huge delay costs and a huge increase from the previous year. And although the future in air transportation seems uncertain at this moment, but we believe over time it will become much better. And due to its complicated nature of this problem as a large-scale mixed integer problem with different objective functions to consider, most of the past work focused mainly on inexact solution methods. And what are we doing here in this problem? We're assigning each flight in a set F to a compatible gate in a set G, and each flight and each gate have their corresponding parameters associated. We're deciding on the gate assignment choices xik and gate times TIG and pushback times TIP, and we're minimizing the total arrival delays, which is expressed in summation over all flights TIG minus AI. And we have shown in our work that this problem is NP-hard. There have been some previous work that showed this problem to be NP-hard with different objective, but we proved this in our setup to be NP-hard by a reduction from a known NP-hard scheduling problem. And here is a compact formulation of our problem. We observe the turn time, the buffer time, and the compatibility requirements in these constraints, and I want to point out the difficult constraint here. For I less than j, and for particular gate k, if I, j are assigned to the same gate k, then the gate time of j is at least the pushback time of I plus the turn time of this gate. This is a difficult constraint and has to be written for all flights that satisfy I less than j and for all gates. So this makes the compact formulation not ideal for a large case. So we did a branch and price reformulation. We used the set covering restricted master problem formulation. And for the pricing problem, we know that not all gates have interactions, so they can be decomposed based on their interactions. So we present the simplest case here. We assume all gates are independent. Now I want to introduce some additional notations. In particular, for each pattern P, we associate a cost CPK with it, and we'll later express CPK in an explicit expression. And here the ZPK denotes the decision variables for this restricted master problem. And here is the standard restricted master problem formulation, and we denote the dual variables by pi I and mu k respectively. Now this is the decomposition of the pricing problem. As we pointed out earlier, if we assume all gates to be independent, then we can pull out the k in set G outside of the minimization problem. We write a pricing problem for each gate. And if we fix k, then the mu k is a constant here, so we can also pull that out from a minimization problem. So this also helps with the difficult constraint, as we don't have to write that constraint for all such gates. We just have to write this constraint for each gate. Now this is a more intuitive way to look at the pricing problems. We look at it from a maximization perspective, and here we explicitly replace the delta IPK parameter with the pricing problem decision variables xik, and we replace CPK by the expression summation over all flights TIG minus AI, which is the total arrival delay. So we have shown that this constraint maximization problems can be posted as unconstrained submodular maximization problems by incorporating some of the constraints into an algorithm to compute the cost. So the idea here is we can pre-process the incompatible flights and incorporate all the constraints into an algorithm to compute its cost, then we don't have any constraints left. So in this way, we can utilize some of the existing submodular maximization algorithms to very efficiently obtain assignment patterns with negative reduced costs. However, to prove optimality, we need to obtain exact optimal solutions for the pricing problem, and we could do this by solver. But however, we propose a much more efficient dynamic programming algorithm based on a recursive formula. So now here we define FIT to be the optimal value for all flights after flight I with a starting time of t. Then based on this definition, we can write a recursive formula for FIT. Then based on this recursive formula, we can develop a dynamic programming algorithm to solve this problem. And we show that if let C be the last time point to consider and all data to be integer, then each function FIT is piecewise linear with at most n square C pieces. And so we can run the dynamic programming algorithm with the time of n cubed C. And we show that it suffices to pick C as the last arrival time plus the maximum of all the pi i's. The idea here is to look at all the possible slopes that a particular FIT can take, then we can bound the pieces from there. And we tested out the dynamic programming algorithm, and it works well up to a certain sized instance. So we propose a rolling horizon method, which implements the dynamic programming in each of its horizon. And we have developed a criteria to determine the optimal horizon size. The idea here is to look at the interactions between flights, and at some point, flight J is independent from flight I, meaning whether we take flight J is independent from whether we take flight I. And in the branch and bound setup, we at each node, we try different pricing problem methods, as we pointed out earlier, and we branch on the assignment decisions. Given the optimal ZPK, we can compute the assignment decisions YIK, then we can branch on that parameter. We also introduce a tolerance parameter here, so we terminate the branch and bound process if a feasible solution is found with objective that is less than 1 plus the tolerance parameter of the root optimal value. And after the root optimality is achieved, we run an auxiliary integer program to obtain a feasible solution just using the patterns that are generated so far and solving the restricted master problem with the binary constraints on ZPK. So we generated our flight sets and gate sets randomly, but we try to replicate the real-world scenarios, and we put 10-hour limit on each instances, and we have selected 6 instances to showcase our results here. And there are 3 small instances, 2 moderate instances, and 1 large instance. So here is the results on the pricing problem methods. We plotted our CPU time in a log scale, and we have seen that our approach using the DP or rolling horizon method plus the submodular maximization approach provide a significant improvement over the standard solver approach, which is implemented in Groby. And we want to point it out in the solver case, instances 4, 5, 6 reach the 10-hour limit. And here is the results on the branch and bound modifications. And again, the plot is in log scale, and we have shown in here that our approach significantly outperformed the standard branch and bound, especially if we have the tolerance parameter and the auxiliary IP setup, the performance is really well. So that's all for the presentation. Thank you.